Hello everyone, this is lecture 8 in the series of Math 120 Introductions to Linear Algebra lectures. Today we will talk about matrix vector product. In this lecture, we will see matrix as an operator that acts on a column vector to create another column vector. The matrix vector product is widely used in mathematics, physics, and computer science. We can use matrix vector products to represent a system of linear equations, and this can be used to determine the solution of the system algebraically or numerically. And this is such an important concept, and that is why it will reappear many times throughout the remaining of the course and in courses related to computational mathematics, data science, and even machine learning. Let's take a look at the learning objectives. So after this lecture, hopefully you could be able to form a matrix vector product and express a system of linear equations in terms of matrix vector product form. So the definitions of the matrix vector product is an M by N matrix A can be multiplied with a vector X with N components. The result is a vector with M component. We can see that the resulting vector is with M components because from last time when we talked about matrix multiplications, that the column dimensions of the matrix on the left has to be the same with the row dimensions of the matrix on the right. So that is why in this case, even though we have the matrix vector product, the column dimensions of the matrix A has to be the same with the row dimensions of the vector X on the right. In general, this is what you can write. So the matrix A acting on the vector X, and let's say you have M by N matrix, so the components are A11, A12 up to A1N. Those are the entries in the first row. And for the second row, you have A21, A22 up to A2N, and so on and so forth. Then you go down to the last row, which is the M row. So AM1, AM2, and you do this up to AMN. And then you multiply with the vector X with N components. So you have X1, X2, up to Xn. And the resulting vectors is going to be so to do this multiplications, you're going to take the first row of the matrix and multiply with the column vector. And this gives us A11 X1 plus A12 X2 up to A1N Xn. And you do the same for the second row and so on and so forth until you get to the last row, which is the M row. For the second row, you have A21 X1 plus A22 X2 up to A2N Xn. And for the last row, you have AM1 times X1 plus AM2 times X2 up to AMN times Xn. And again, because this is the M by N matrix, and this matrix is acting on the column vector, and for the column vector, the dimension is N by 1 vector. Right. So the resulting vector should be M by 1 vector, and therefore you have M row or M component. Okay, so this is the definitions of the matrix vector product. It's very similar to the last time that we did when we do the matrix multiplications, right? It's just that on the matrix on the left is going to be the same, but instead of a matrix on the right, now you just have a column vector. Okay, now let's take a look at the examples. Hopefully it should be straightforward. So we have a 3 by 3 matrix acting on the column vector. So this is 3 by 3, and this is 3 by 1, and the resulting vector should be a 3 by 1 column vector. Okay, so what you can do is that for the first component, you're going to take the first row and combine with the column vector. You have 3 times 2 plus 0 times 1 plus -1 times -7. For the second entry, you take the second row of the matrix and combine with the column vector. You have -5 times 2 plus 2 times 1 plus 4 times -7. And for the third component, you take the third row of the matrix, combined with the column vectors. You have 1 times 2 plus -6 times 1 plus 0 times -7. And if you do the calculations correctly, this is what you're going to have: 13, -36, and -4 for the entry. Okay. Now moving on to the next example, you have a matrix A. So this is 7, -4, 2, and -1, 0, 6. So this is a 2 by 3 matrix. And this matrix is acting on a column vector. And this column vector is 3 by 1 column vector. And the resulting vectors that you're going to have is a 2 by 1 vector. So A acting on or multiply with vector X should result in a 2 by 1 vector, or 2 by 1 matrix for that matter. So A times X is equal to the matrix A has the entries of 7, -4, 2, -1, 0, 6. And this is acting on the column vector 3, -5, 1. So this is what you get, right? So the first entry is going to be 7 times 3 plus -4 times -5 plus 2 times 1. For the second entry, you take the second row of the matrix and combine with the column vector. You have -1 times 3 plus 0 times -5 plus 6 times 1. And the resulting vector should be 43, 3. And again, at the beginning, I briefly mentioned about an operator, right? Because A is acting on a column vector, so A is sometimes called an operator. Just like when you take calculus, the derivative is an operator on the functions, or the integral is another operations that act on the functions. So in this case, A is an operator that's take on or acting on the column vector. We always have a matrix vector product where A is on the left of X, or X is always on the right of A. So using the matrix vector product, we can actually form a system, or if you have a system of linear equation, you can use matrix vector form to rewrite the system. So definitions: a system of the form A11 times x1 plus A12 times x2 up to A1n times xn equal to B1. So in this case, the A's are the coefficients and the B's are just some constant, right? So the next equation should be A21 times x1 plus A22 times x2 plus A2n times xn equal to B2. And you can do this for m linear equations or m components. So you have am1 times x1 plus am2 times x2 up to amn times xn, and this is equal to b sub m. Okay, b sub m, because again you have m component or m linear equations. So a quick note here, you have m linear equations. And again, the b's are constants and the a's are the coefficients. They should be constant as well. And in this case, the system have m linear equations and n unknowns. Okay, so a system of this form of m linear equations and n unknowns can be written in terms of matrix vector product as follows. So what you have is you take all the coefficients and put that as the coefficient matrix. And all the variables, so you have n unknown or n variables from x1 up to xn, and you put that in the column vector. And the right-hand side consists of all the constant b1 to bm. That is a constant matrix or constant vector. Right. So all the coefficients you put in the coefficient matrix is a11, a12 up to a1n. That's the first row. The second row is a21, a22 up to a2n, and so on and so forth up to am1, am2, and amn. So again, this is a coefficient matrix. All the unknowns you put together, and you have a column vector from x1, x2 up to xn. And the right hand side is the constant matrix or the constant vector is b1, b2 up to bm. This is called the coefficients matrix. This is the unknown vector. And the vector on the right, this is called the constant vector. And later on, we will use this kind of setup. In the matrix vector form, you can write A acting on X, or A times vector X is equal to a vector B, and you can find the unknown or the variables very easily by finding the inverse of the matrix and multiply the inverse on both sides of the equation. You will be able to obtain the value of the unknowns fairly easily. But that is for the later lecture. But for now, hopefully you get some idea of how to form a matrix vector form from a system of linear equations. Okay, now let's take a look at some similar example. Now in example 3, we could like to write the system of linear equations in terms of matrix vector form. And again, what you do is the matrix vector form consists of a matrix A, which is a coefficients matrix. Vector X consists of all the unknowns, and vector B consists of all the entries on the right-hand side of the system, or the constant vector. Right. So here, the coefficient matrix consists of the entries of 3, 5, 1, and 4. So this is a 2 by 2 matrix because you only have 2 coefficients for each equation. And there are 2 unknowns, x1 and x2. So this is a column vector, x1, x2. equal to the right-hand side vector, which is the constant vector, consists of -1, 2. Again, this is the coefficients matrix. And this is unknown. And the right-hand side is the constant vector. Okay. Now for example 3, in this example, you have a system of 3 linear equations with 3 unknowns. So that means the coefficient matrix is going to be a 3 by 3 matrix. The unknown will be a vector of 3 rows, or the 3 by 1 vector. And the resulting, or the right-hand side, the constant vector will be a 3 by 1 vector as well. So now let's write down the coefficient matrix, which consists of 5, 0, 1. Right. So the 0 in the place of x2 because there's no x2 in the first equation. In the second row, or the second equation, consists of the entries of 0 because there's no x1 in the second equation, 2 and 3. And in the last equations, you have 2, 1, and -4. This coefficient matrix will act on the column vector x1, x2, x3 to indicate that there are 3 unknowns in the system. And the right-hand side is the constant vector, consists of -1, 0, and 2. So again, we just see that a system of linear equations can be written in terms of the matrix vector form. And from here, you have a very important theorem that the system in terms of the matrix vector form is consistent. That means there exists solutions if and only if the vector B, or the constant vector, is a linear combination of the column vectors of A. Right. So this theorem is called the existence of solutions of the system. Okay. And again, the system is written in terms of the matrix vector form. Okay, so the theorem is AX equal to B is consistent. So again, a system is consistent when it either has a unique solution, or exactly one solutions, or infinitely many solutions. Okay. So the system is consistent if and only if the vector B, or the constant vector, is a linear combination of column vectors of A. All right, so let's prove this theorem because it's quite important to see the existence of the solution in the system. Okay, so because we have an if and only if statement, it's good to break the proof into 2 parts, the forward direction and the reverse directions. Okay, so in a forward directions, that means you assume that suppose there's solutions to the system, and you want to show that the constant vector is a linear combination of the column vectors of A. In the reverse directions, we first need to assume that B is a linear combination of the column vectors of A, and therefore we need to show that the system has at least one solution. Okay, so first let x equal to x1, x2 up to xn be a solutions of the system AX equal to B, where A can be written as V1, V2 up to Vn. So the V's here are the column vectors, where V's are the column vectors of A. Right. So we first assume that the system is consistent. So at least the system has A solutions. Okay. So now you write that AX equal to B, or it can be written as V1, V2 up to Vn. And this matrix is acting on the column vector x1, x2 up to xn. And this is equal to B. Okay. Now remember, the vector x is a solution, is already considered as the solutions. Now, using the matrix vector form, you can write this as x1, v1. Sorry about this. So v are vectors. So x1, v1 plus x2, v2 up to xn, vn. And this is equal to the vector b. So this showed that B is a linear combination of the column vectors of A. Remember, the x1, x2 up to xn are some constant or some solutions of the system. Right. So this shows that B is a linear combinations of the column vectors of A. Right, so that's the forward directions. Now the backward directions or the reverse directions. Conversely, we write A consists of the column vectors of v1, v2 up to vn. And suppose B is linear combinations of the columns vectors of A. Then there exist the coefficients. Right, so by definitions of linear combinations, there exists some coefficients C1, C2 up to Cn, such that you have that C1 V1 plus C2 V2 up to Cn Vn equal to B. And because we say that there exists some constant or coefficients C1 up to Cn, C1, C2 up to Cn is actually a solutions of the system, right? Because you can rewrite this as A acting on C1, C2 up to Cn, and this is equal to B. And we already say that this C1, C2 up to Cn exist. And therefore, this is a solution to the system AX equal to B if we write this as a vector X. Right, so again, this theorem we just proved is that the system always has A solutions if and only if B is linear combinations of column vectors of A. Okay, which led us to a next theorem where we have a multiple statement and they are all either they are all true statements or they are all false. Okay, so let A be a M by N matrix, then the following statement are logically equivalent. That is, for a particular A, so for some matrix A, either all statements are true or they are all false. Right. So the first statement is that for each constant vector b in Rm, so this means that this is a column vector and it has m component or m rows. The equations ax equal to b has a solutions. Right. So this statement we already proved that. So we already proved this statement earlier, right? So where we say that this equation ax equal to b is consistent even only if b is linear combinations of column vectors of A. Then let us to the next statement. So for each b in Rm is a linear combinations of the columns of A. And because of this, the columns of A span Rm. Right, so go back to definitions of the span of a set of vector. And in this set consists of all the column vectors of A, right? And the column vectors of A span Rm because the span consists of is the set of all the linear combinations, right? And the linear combinations that we can form is actually the constant vector B. And the constant vector B is in Rm. The set of all the columns of A span the entire Rm. And the last statement is that A has a pivot positions in every row. Because the equation has the solutions, there is always leading one in every row in the vector A, right? So the pivot positions indicate that there is always a leading one in every row of the matrix A. All right, so we're not gonna show the proof because this is just logically equivalent to one another. Right, but we're going to move on to the next definitions where we want to see the homogeneous system. The homogeneous system occur when the right-hand side of the system are all zero, or the constant vector is a zero vector. So a system of linear equations is called homogeneous if the constant vector is a zero vector. In other words, or the constant term in each equations of the system is zero. So consider the following example. You have the system of the form 2x plus 3y minus z equals 0 and negative x plus 5y plus 2z equal to 0. So this is a system of two equations with three unknowns, and you can see that the right-hand side is equal to 0. Okay. Also, we can consider the system x plus y minus 3z equal to 0 and minus 3x plus 2y minus z equal to 0 and 2x plus y minus 4z equal to 0. So this is a system of three linear equations with three unknowns. The right-hand side or the constant term in each equation is 0. So this is a homogeneous system. For homogeneous system, some note here. So homogeneous system has either one solutions or infinitely many solutions. So we're not going to show that. It's just a note I want to give you. I want you to know that the homogeneous system is always consistent. So that means it's always either or has always either one solutions or infinitely many solutions. There is no homogeneous system that has no solutions. Okay. The second note is if you have an augmented matrix, right, consists of the coefficients matrix and the constant matrix, is a homogeneous system of M linear equations with n variable where m is less than n, then the system has infinitely many solutions. And when m is greater than or equal to n, the system has either a unique solution or exactly one solutions, or infinitely many solutions. Okay, so now, so there are two cases for the homogeneous system, right? So when the number of equations is less than the number of variables, then you can conclude that the system always has an infinitely many solutions. Okay, now when the number of equation is greater than or equal to the number of unknowns, then the system either has a unique solutions or infinitely many solutions. Okay, go back to the example we see earlier. So in this system, you have two linear equations and three unknowns. So two equations, three unknowns. So m is less than n, and you can conclude for this particular system that there's always infinitely many solutions. And for the system on the right, you have a system of three equations, right, with three unknowns. So that indicate that the system either has one solution, exactly one solutions, or infinitely many solutions. So that means you have to work out the details to see if the system has just one solutions or infinitely many solutions. So we note here either one solutions or infinitely many solutions. Okay, so it depends on the problem and you need to work out the details to see that. The last topics I want to cover is called the linearity properties of the matrix vector product. And again, when you talk about matrix vector product, the matrix is considered as an operator, right? So you want to see how the matrix operate on this column vector, right? So let A and B be matrices, X and Y are vectors, and C is a scalar. So A plus, if A is acting on the sum of the two column vector, this is the same with This is equivalent to A acting on the column vector X, then added with A acting on the column vector Y. So this is acting on the left. The second note or the second property is A plus B times column vector X. So in a way, you can distribute X. So that is AX plus BX. Again, if X is on the right of the vectors, then after the distribution, X is still on the right of the vector. In the first case, if A is on the left of the vector, then after the distribution, A is always on the left of the vectors. The last one is the scalar multiple, right? So if A is acting on a scale versions of the column vector X, then what you can do is you do the matrix vector product first and then do the scale, because the matrix vector will give you a vector, and you can scale the resulting vector. Okay, so that's it for me today. Please let me know if you have any questions. Thank you.